चालू है अपना लगा दूं तो मैं इसको वाला ठीक है ना क्वालिटी के हिसाब से
Again, good morning. Welcome to this second day of CANDEE, and we are starting with this technical session where there are two talks. One, the keynote talk is by Professor Aparab, and another is plenary talk by Dr. Ajay Mishra. So may I request Dr. Pinsu to chair the session, please. Professor K.S.K. Sinha was supposed to be here, but he is arriving a bit late.
Thank you, Professor Aruna. It is my honor to share this session. So, this morning session, we're going to start with Professor Brown. So, let me introduce this a little bit. Okay. Professor is a very, very kind person. Yesterday, he shared my session, and he encouraged students to ask a lot of questions, which is very nice. And I'm really, really appreciate his support as well. So let me introduce him a little bit. Okay. Right now, he's Robert A. Bowen, endowed professor in the Department of Physics at the Astronomy at the Clemson University and founding director of the Clemson Nanomaterial Institute. He's known for developing Raman spectroscopy into a versatile tool for characteristic carbon nanomaterial and developing liquid injection-based synthesis method for the carbon nanotubes. And right now, his research at the Clemson University focused on many applications of the carbon and other nanomaterial in the energy investing material technology as well. So without further ado, please give a warm welcome to the professor.
Someone should go there.
Good morning. Okay. So can all of you hear me at the back? Okay, great. So very good morning to all of you. So I'd like to begin by thanking Anurag for taking this amazing project and his team, the organization team. So thank you for having me here so that I can tell you a little bit about the work we are doing at the Clemson Nanomaterial Institute. So this institute still sits at the university level. So as most of you know, you have the department. Department is under a college, right? Like physics is. So physics is under College of Science, and then College of Science is under the university. So this sits at the university level, and therefore we are a very collaborative environment. And these are the different topics that we work on. So there are basically 4 broad topics: multi-scale modeling, energy storage, which is what I'm going to talk about today. And then we have energy harvesting, and then we have biomedical applications. And we are funded by several different agencies, and I want to acknowledge this funding stream because without their support, nothing moves forward, right? Now I need to add spark on this one, which is missing. Yes, I need to do that. And then I have my team. This is my team working on different aspects of the research at CNI, Clemson Nanomaterial Institute. And today's talk will be from contributions made by Dr. Mihir Parekh, who is a postdoc in my team, Professor Binghan Lu, with whom I work. He's in China, he's a battery expert. And then Professor Sabat, who is in my team, and students, Janak and Peshab, who are part of my team at Clemson University. Okay, so I usually mention the acknowledgement first because I always run out of time. So please give me a 5-minute warning, and then you don't acknowledge your team members. So I want to get that out. So I thank them for their hard work. So a question to the students: when you think about Thomas Edison, what comes to your mind? What's the first thing that comes to mind? A light bulb, right? Yeah, that's the right answer. But you know, he also had 1,000 patents, 1,000 patents, more than that actually. And he is also the inventor of the electric car, and not many people know that. So if the question is when was the electric car first invented, it's 1895, more than a century. But unfortunately for Thomas Edison, what happened is that Henry Ford's first Model T internal combustion engine then hit the manufacturing line. Okay, so you see that it's only about 10 years, right? Little over 10 years, 13 years to be precise. In 13 years, the whole world changed for Thomas Edison, and nobody ever bothered about the electric car. Right? So since then, electric cars are trying to come back in a big way. And today, of course, Tesla is there, and there are many other companies. And trying to bring the electric vehicles back into our commuting stream was first taken up by General Motors. So General Motors in 1996, that's the car that they advertised, but it was not economically viable. So it didn't see the light of the day. So now, this thing did take off. Yes, and so yeah, ever since this electric vehicles have been trying to come back, and now, of course, everything is working on wireless. Wireless devices are powered by batteries, and the king of all batteries is the lithium-ion battery. And the reason it is the king because it can deliver a lot of energy compared to potassium-ion batteries or sodium-ion batteries. Okay, so everybody likes to use lithium-ion batteries. And so this begs the question, why did lithium-ion batteries all of a sudden become viable? Right? And the answer is innovation in materials. So the materials in the past 3 decades have taken off so well, especially nanomaterials, that the energy density increased 3 times, tripled. As it is, lithium-ion batteries give a lot of energy, like I mentioned. You can actually triple it, and then the cost has decreased 7-fold. Okay, and what exactly are the materials that enable these kind of things? It's the graphite anode. Graphite is very cheap, right? Graphite anode, and then you have the cathodes. There's a whole family of cathodes, many more elements in the cathode side than the anode side, as you can see on the screen. And then, of course, there are polymers that separate these two electrodes so that they don't short circuit, right? And then you have electrolytes, and electrolytes have the salt and the solvent, right? Basic chemistry. So all these advances in the past 3 decades now even embolden us, or we can even start thinking about electric vehicles and lithium-ion batteries. So whenever I give talk on these batteries, the first question the audience asks me is which electric car I'm driving. And the answer is I'm still not driving an electric car because I think the materials need to improve even more. There's high potential, and that's what I'm going to talk about in this presentation here. Okay. Let's see. Yes, that's the right one. So the title was Sustainable Batteries, and this figure very nicely shows what is the problem with lithium. If you look at this bar here, it is the crust abundance of alkali metal in Mother Earth, okay, in the crust of Mother Earth. So it is, lithium is about 0.0017%. So try to wrap your head around that number. It's a very, very small fraction of the Earth that is lithium. Okay, and then if you look at potassium, which is here, it is more than 1. So there is a break in this axis here. Okay, so this is more than 1, and of course sodium is a lot because we have a lot of ocean, right? And sodium is very abundant, 2.3% of the Earth's crust. So in order to have sustainable batteries, we need to start working with potassium-ion batteries, sodium-ion batteries, and so on. But because of the interest of time, I'm going to just present about lithium-ion batteries and potassium-ion batteries. Okay? And I'll be using this interchangeably during my presentation. Okay, so before I show you what a battery is, let's look at how a battery really works. So what happens is when you prepare a battery in the lab, like I showed you, the oxides, cathodes already have the lithium or potassium in it. Okay, and then when you charge your vehicle, or as you see in this cartoon, the vehicle is being charged here now. When you're charging, what happens is the ions travel across the separator. This is the separator. The blue part is the electrolyte, and they lodge themselves in the graphite anode. Okay, and when the vehicle is fully charged, then you use it, and the electrons flow in the external circuit. Those are the yellow dots, and then they come back to the host cathode. So this is how it works. And of course, electric vehicles, all of you know, it needs overnight charging, right? You have to plug it in, and you can use it the next day. So why is that? So the reason that is the case is because we are using graphite, and graphite is a layered material, as you can see here. The black sheets are hexagonal graphite, and as the battery is charging, the lithium ions go through what we call a staging process. Stage 3 means there are 3 carbon layers between the alkali metal layers. The alkali metal layers are the purple ones. Okay, so it has to go through stage 6, 5, 4, 3, 2, 1. And that's why charging these batteries takes a lot of time. Okay, and if you try to charge it very fast, of course the battery heats up and then it catches fire, which is what you don't want, right? So how do we solve this problem? So in the 90s, if you are following carbon literature, there have been new forms of carbon other than graphite and diamond. Graphite and diamond are very well known for several decades. But then you have fullerene, which is up here. It's like a soccer ball shape, right? All carbon atoms. Then you have nanotube, and then you also have one single layer of carbon, which is the graphene, which you see there. So this begs the question: can these carbons help us make better battery? Okay, so to address that, Bing and Lou at Hunan and myself, we teamed up to see if we can make a better battery. And obviously, the graphene is the best. Why? Because we want all the alkali metal ions to be interacting with carbon ions or carbon atoms. Like this is not preferred. This is dead carbon. It's not interacting, right? So we want every layer of carbon to interact with the alkali metal. So how can we accomplish that, right? So we came up with something called few layer graphene microspheres. It's in the title, FLGM. So basically, I'm not going to bother you with the synthesis method. If you're interested, the reference is down there. In 2021, we published this. So basically, it's a decomposition of tetraphenyl 10 using sulfur as a catalyst. Okay? Pure chemistry. And then you can make these nice fuzzy microspheres, and then if you zoom in, you can see these nice graphitic sheets in there. Okay? And if you zoom in even closer, you will see it is not single layer graphene, it's a few layer graphene, as you can see over here. About 3 to 5 layer graphene. And this structure is very beautiful. Why? Because now when you're charging the battery, all the sheets of graphite are radially distributed, and they are like with open arms embracing the alkali metal to come and interact with them. Okay, so you can think about fast charging batteries this way. You don't have to go through the staging process anymore, like we did it in graphite. Yeah, so this is a very exciting discovery. And though the first thing, of course, we can look in the high resolution PM as we are seeing here, and there are few layer graphene. And on the previous slide I showed you, they are in the same shape of a microsphere. But then, is it really carbon, right? So the best tool, thanks to Sir C. Raman, right? Raman spectroscopy is the best tool to study carbon, whether it is fullerenes, diamond, graphite, anything, graphene, because it has a very specific fingerprint for each of those forms of carbon. And you can see in this graph here that graphite has this, what we call the G, or the graphite-like band. And then if the graphite has a disorder, we have the D band. And then 2 times this is shown here, the 2D band. Okay? And in the literature, you will find that in order to scale up graphene production, chemists have worked with graphene oxide, and then they try to reduce it. And they call it reduced graphene oxide. So GO is graphene oxide, RGO is reduced graphene oxide. But clearly you can see that reduced graphene oxide is much, much, much inferior than graphite or the few layer graphene microsphere, which is the topmost spectrum. So you want very sharp, narrow peaks like you see there. And again, this is a little bit of detail. When the height of this band is more or less the height of the G band or the graphite band, then you have a few layer graphene microsphere. So we have verified this visually as well as with spectral fingerprint that this is indeed few layer graphene. Okay, so what do we do next? So we can now take these microspheres and make a slurry. So we make a slurry by adding some additives like CMC or carboxymethyl cellulose and a little bit of carbon black to improve the conductivity. And then the slurry is spread over copper foil or an aluminum foil, depending on what type of battery you're making. And then we dry it. And then we basically use that as the cathode or the anode, depending on again what type of a battery. And then we use a counter electrode. If it's a potassium ion battery, we use potassium. And then we use a separator. And then we assemble them into a coin cell. So this is basically a coin cell. So you have the bottom case and the top case. And in between, you put the cathode, separator, and the anode. Okay, and then you have to do all this inside a glove box. Okay, and once it is hermetically sealed, you bring it out of the glove box and you can do some testing. And what kind of electrolyte? This is a potassium-based salt. It's potassium. It's KPF6. Okay, and in these solvents, ethylene carbonate, dimethyl carbonate, and so on. And these types of cells are called 2032 cells. Okay, so here are some of the glove boxes in my lab, and we also make the pouch type batteries, which is up here. These are larger format. And this is some of the batteries testing stations in my lab. You can see pouch cells are being tested there. Okay, so this schematic is same as that animation I showed you. Now, before I show you the data, I want you to understand some terminologies. I'll be talking about them over and over. So this again has it has the cathode here with the alkali metal ions here. This is the graphite separator and so on. Exactly same as the animation. So first thing, battery experts look at is something called Coulombic efficiency. So how do we define Coulombic efficiency? Coulombic efficiency basically means the number of potassium ions that left the cathode and went into the anode during charging, and this number of potassium ions that were returned. Okay, so you want this process to be close to 100%. All right. So again, for the students, 95% or 98% is outstanding grade, right? But for batteries, 98% is a fail. Can anybody tell us why?
Number of discharge cycles.
Sorry?
Discharge cycles.
Yes, because every cycle, if you're losing little by little by little, then you don't have, eventually by the time you reach hundreds of cycles, you don't have enough lithium ions or potassium ions moving. So the Coulombic efficiency has to be close to 99.9 or 99.8%. Okay, that's the kind of benchmark that we have for batteries. Okay, then the other thing that you will hear me talk about is capacity. So capacity, as the word says, is ability, how much ions it can store, how much ions the electrode can store. And the unit for capacity is milliamp hour and H per gram. So basically it is coulombs per gram. So if I have certain rate of anode material, how many coulombs it can hold. Okay, so that's another important number. Okay, so these are the two things, and there is one more, there are two more actually. The other terminology I'll talk about is called the C rate. C rate means how fast the battery is charged or discharged. Okay, so 1 C means the battery is charged in 1 hour or discharged in 1 hour, and 0.5 C means it takes 2 hours, and 2 C means it takes only half an hour. Okay, so a battery which 2 C you can charge and discharge in 1 hour, because 30 minutes for charging, 30 minutes for discharging. So that's another number to remember. And then the last one is how in the world do we know what capacity to expect when we make this battery? Okay, that is given by this equation here. So where these terms X is the number of electrons transferred in a reaction. So let's take a simple reaction, like lithium giving up its electron and interacting with carbon to form LiC6, right? So here you can see one electron has been exchanged, so X is 1, and the Faraday constant is a constant, it is given there, 96,485 coulombs, and N is 6 carbon atoms and 12 is carbon's atomic weight, right? So if I'm making an LiC6, then I should expect about 370 milliamp hour per gram based on that chemical reaction. And if I do the same thing for potassium, it is about 272 milliamp hour per gram. Okay, so these kind of calculations can be done. And so let's see how few layer graphene does compared to the other forms of graphene. So what I'm plotting here is the capacity versus cycle number. And I'm comparing the few layer graphene data, which is black curve, and the red data points. Black is during discharge and red is during charge. And you can see they beautifully overlap one another. You can barely see the black data and the red data. They overlap beautifully. And so you can see that if I pump more and more charging current, I go from 100 to 200, 400, 600, 800. So I'm pushing the battery to charge faster. The capacity takes a hit. It starts off at 250. Yeah, I just told you that we expect around 270, right? So 250, this is the potassium ion battery. So we expect that 270 starts off at 250, and then by the time I reach thousands of cycles, 1000 milliamp per gram, very high charging current, then it is holding above 100. Right? But look at the other forms of carbon. Right? If you take commercial graphite, or graphite itself, by the time they are charging very fast, they almost cannot hold any charge in it because they don't have the capacity. They don't have these nice radially outward fins like the few layer graphene microscope. So the point here is we can get very nicely, very reversible capacity, and this goes back to the same figure I showed you. You don't have to go through staging process, and then you can fine tune this a lot more. You can then go to 3000 milliamp hour per gram. So that is like charging this battery in 6 minutes. Okay, it's 10C. 10C is charging in 6 minutes. And you can see, you can cycle up to 10,000 cycles. Yeah? And that is because carbon bonds are covalent bonds, they're pretty strong bonds. But in comparison, if you look at commercial graphene, they are close to zero. Yeah? And graphite is almost zero, and the battery dies actually. It died here, and that also died there. And so this few layer graphene microsphere is a new material. And we have shown that you can make lithium-ion batteries, aluminum-ion batteries, sodium-ion batteries. It works for all kinds of batteries. Okay, so this is exciting results. So what's next? What's next is we know that graphene has spurred a lot of interest in other 2D materials, right? And a snapshot of that is in a nice review article, which is cited here on the screen here. There are many 2D materials. And we heard about some of them yesterday. And here is a laundry list of them, right? So all of these are potential candidates. So we'll need an army of students and postdocs to test everything, right? So in order to, because that is not feasible, so that's why we are now trying to leverage machine learning, AI, and all these tools to see which one of this has a better chance at finding an electrode that can hold a lot of charge, high capacity, and can charge very quickly or discharge very quickly. Okay, so this is where the field is heading. Okay, so now I'm going to shift gears and talk about, I showed you the anode family is very weak, right? Only graphite was listed there. And the cathode family had many elements in it, right? Many oxides were there. So how can we improve the energy density? One potential element that can serve as a graphite anode or a battery anode is silicon. Okay. So why do we need to bother? Because currently, if you look at an electric vehicle, it's 26% or almost 1/4 of the vehicle's weight is the battery pack. It's pretty heavy. And this is a big problem because if an electric vehicle hits an internal combustion engine vehicle, the latter one gets battery damage because it's being hit almost like a 18-wheeler, a heavy truck. So the idea is to try to use lesser and lesser amounts of battery in the battery pack and still make the car go thousands of kilometers or miles. Yeah? So how can we do that? The only answer is you have to reduce the number of batteries, which means each battery should be more powerful, a better battery. Right? So silicon, like I said, has a potential because it has high specific surface area. Semiconductor industry is well established, so commercial scale is available, right? So economically viable material. And if you then, like I showed you with the KC's, the LIC6 example, first thing is to calculate, do a simple calculation to see how much capacity silicon can provide, right? So KC8, well, let's talk about LiC6 first. So each carbon atom holds, 1/6 of a lithium ion, right? So 1/6 of a lithium ion. So it can bind only 0.16 lithium. KC8 can bind even less, 0.12 potassium. But if you bring silicon into the game changes. Why? Because one silicon can hold 4 lithium ions. It's the reverse now. Right? So this number is huge, almost 4 lithium ions, because it forms that compound. All right. So this is all good, but then how do we bring silicon into the material processing aspect? Because it's a semiconductor. It's not a conducting. It's not conducting electrode material, right? So here is a list of comparing carbon versus silicon, the merits. So the density is about the same. Theoretical capacity, I told you already this is 372. But if you do the calculation like I showed for KC6, this is more than 10 times. Right? You can get huge amount of capacity, which is good, which means you don't need to make the whole electrode out of silicon. You can add about 10% silicon, still you will make a much better battery. Okay, so that's the idea. And then every good idea is playing with a lot of challenges. So here also we have a challenge, which is that when the lithium ions or the potassium ions go in the gallery space in graphite, it swells about 10%, 15% or so, because the interlayer spacing changes. With silicon, it is 300%, more than 300%. And that is a huge, huge problem which the battery industry is still trying to solve. Okay? And toxicity is not an issue with silicon or carbon. And the 300% volume expansion then leads to what we call polymerization, because every time you start with the silicon atom, let's say here, or silicon compound, lithium silicon compound, you lithiate it, delithiate it, and it just keeps fracturing, right? And then there is another important parameter which I haven't mentioned at all. It is called the solid electrolyte interface, SEI, and I won't have time to talk about that, but SEI is very critical for stable operation of a battery. Okay, but when the lithium sulfur compound fractures, the SEI breaks, as you can see in this cartoon. It breaks, and then new SEI has to be formed every time, and that is not desirable because the SEI formation takes lithium or potassium, and then your coulombic efficiency starts to go down, right? So you don't want that either. And then the other problem is, because of expansion, there is delamination. It will get detached from the current collector, which is shown here in the red. So how can we solve this problem? The first answer that comes to mind is use nanosilicon, right? And nanosilicon is commercially available, and the best nanosilicon is silicon, which is about 30 nanometers in size. So we purchased some of that, and we made a slurry and we made a battery. And sure enough, we get very high capacity, compared to 370 or 250, we are up there, 1500, which is wonderful. But the problem is, because of these three challenges, see, the capacity is almost dropped by 1/3 by the time you reach only 30 cycles, which is not a very good battery. So this is a good battery if you have only one-time use or a couple of uses. But if you want to use this for electric car, which we should because it has very high specific capacity, this is not a good battery, right? So how do we fix this problem? So there are a lot of brilliant minds around the world. So they tried making silicon nanowires, nanoparticles, hierarchical structures. I won't go into all these details here. The carbon encapsulation, and they've tried a lot of things. And if you want to read up, that's a nice Nature Review materials published by another team. But long story short is we innovated a material that we call silica nanoquill. Silica is SiO2, and we called it a nanoquill because when we first synthesized this with the hydrothermal method, and we looked under the microscope, it looked like a blob with all these things sticking out, and it reminded us of a porcupine quills. So that's why we call this silica nanoquills. Okay. Now you can take this and then you can do an Mg reduction and convert them into silicon nanoquills. And the beauty of this structure is it has a hollow core, and you can see that over here, and you can also see that in this high resolution images. And the wall also is porous. The wall is also porous. So what that does is basically when it expands 300 times, 300% or 3 times and contracts, there is room for it to breathe. There is a hollow core, and then also there are pores in the walls, as you can see in this image. So this type enables batteries to cycle much longer than the 30 nanometer silicon particles. And here is an example of that. So this is silica before the Mg reduction, and you see we have gone up to 200 cycles with a fairly stable capacity. So here it is plotted as areal capacity rather than gravimetric capacity, but the point here is stable cycling of the battery. Coulombic efficiency is close to 100%, which is what we want. And then you can then take this silica nanoquill and coat it with carbon, then it does even better, and so on and so forth. So this is a dramatic improvement over this case, right, where the commercial silicon just dies very rapidly, and therefore we have patented this technology, and the patent details are right there. Okay, now I'm going to shift gears. So this is a new form of making a new type of very useful battery anodes, right? Now I'm going to switch gears and talk about a little bit about cathodes. What are the challenges there? So I'll be taking potassium ion battery as an example, PIB, and one of the materials that is very well known is what we call the Prussian blue. So it has potassium, manganese, iron, and so on. So I just refer to that as KMNF. And look at this structure here. So the legend is right here. Potassium is that red ball in there. And battery people like these kind of structures because it is porous. And as we heard from Professor Ahuja also, that this open structure is nice because ions can zip in and out very quickly, right? So people like this. But there are challenges here. So the challenge here is that when potassium leaves this cage, here, then it sort of breaks up, dissolved in the electrolyte. Okay, the manganese gets dissolved, and this framework is not robust and it leads to breakage. Okay, so how do we solve this problem so that you can actually, when potassium goes in, keep the cage robust? So a lot of researchers before our work tried to make these bonds stronger, etc., etc. But really, the solution is not in improving this structure. The solution is actually in improving the electrolyte. So what we did was we made a very smart electrolyte. And the smart electrolyte, what we put a little bit of ferric ions in there. So when potassium goes in, the ferric ion also goes in and stabilizes the spot where manganese is missing, and then holds the cage intact. And I will skip, in the interest of time, I'll skip these slides here and just show you the data. So you can see we can cycle up to 6,500 cycles by this small trick. So most of the time you have to think out of the box and not just, like this is the classic example. You don't work on the cage, you work on the electrolyte, okay, to fix the problem. Again, these details I'm going to quit. Okay, and I'll just show you two videos and I'll end, short videos. So we made, current electrolytes, they catch fire, and this is the newly engineered electrolyte with big and blue, where they don't catch fire. I want to show these two short videos and I'll end my talk. Oops, sorry. Okay, so this is a traditional electrolyte. Oh, okay. All right, let's see. Okay, I'll play it this way. Okay, so traditional electrolyte, if you squirt on it, see the flame just flares up. This is why batteries catch fire, because they are organic electrolytes, and you see it. And so when a vehicle is involved in an accident or overcharging or discharging very quickly, that's where it catches fire. But if you use our engineered electrolyte, then what we find here is when we do the same experiment, this electrolyte is self-extinguishing. So immediately stops the fire. So these details are also published. And then we also did what we call a nail penetration test. So we actually made a pouch cell and punctured it. It does not suffer thermal runaway. In other words, it goes up. The temperature does increase, but then because of what you saw in the second video, it just comes down again. So with that, I'm going to stop here, and again, thank everyone for patiently listening and your
Thank you, Professor. He gave a very nice presentation on the sustainable battery and give the way to modify the graphite anode into the to make even better batteries in the future. So what I can say is that if someday you buy EV cars, I will follow. Okay, so it's a question session. So if anybody have any questions, please focus. Anyone have the microphone?
Okay.
You can hear me?
Yeah.
So very nice talk, Papa. I was just following all that slides. So with the interest of time, I'll just answer three questions. Hello.
Yeah.
So all that battery stuff, whether it is silicon or lithium, whatever it is, the question always arrives: why this Tesla or all this car manufacturer, they are not thinking about it? I mean, you see that he purchased whole plant in the whole land in the Texas. Tesla lithium might be lower. Just focusing on lithium. He's just focusing on lithium recycling, new way to make lithium. Why not? Like he's thinking about sodium, potassium, or do you have any contact with the industry and you can see that they are also interested in this type of technology? Because in the lab scale, they work very well. In fact, when it goes for actual industry, sometimes they suffer.
Okay, so for the benefit of the audience, I'll repeat the question. The question is, why is Tesla interested in recycling and trying to recover the lithium rather than focusing on potassium and batteries and so on? And then why are they not also interested in electrolytes that don't catch fire? So they are interested in these kind of electrolytes, but the shift has been to what we call solid electrolytes. So it has been sold to the battery world as solid electrolytes don't catch fire because they're made out of ceramics. They can withstand high temperature. But the problem is they do still suffer from short circuits because ceramics have grain boundary defects and the dendrites go through the defect and eventually short it. Okay? So coming back to why they are not interested in potassium or sodium, because Tesla wants mobile energy. They want to drive a car. But there are other applications where you don't need to drive, you don't need mobile energy. For example, this auditorium, I could have a battery bank sitting behind this and they could be potassium batteries. Because to get the same energy, I will need more potassium batteries because the capacity it can deliver is less than lithium. But who cares? It is sitting there, right? So such applications are taking off. For example, if you look at windmills are all over, and that only when there is wind it produces electricity, so you have to store it. So those are ideal applications for potassium and sodium ion batteries.
Thank you so much.
Please.
Thank you for a nice talk, sir. Sir, I have recently started working on the anode of the battery, transition metal oxide anode and the silicon anode also. But very often I come across a question that why do you want to work on anode first? Because this graphite anode has a capacity of around 372 milliamp per gram. And this cathode is the limiting factor. It has a capacity of 250. So in no way we cannot, if we use NMC or LFP, we cannot be able to go to 270 or 250. So even if we have a node of higher capacity, then the answer I search and I look at it is we can answer it in terms of volumetric capacity. That we will have good volumetric capacity. We use silicon, and this weight capacity, gravimetric capacity, we cannot change it either by using silicon or graphite. So is there any other way to answer this question? Because most of the things they say that cathode is the limiting factor. First you should go for a cathode. You have limit there, and even if you increase this thing, then this is the produce. So beside volumetric, we can also say something else regarding this.
Yes, that's a very good question. So this question is for battery experts. We have to, so the cathode and the anode should have the same or close to similar capacity because that way the charge can be handled better, right? So the cathodes don't have like what you saw in the case of silicon, very high capacity. That's why. So there are two solutions. One is you have to find a similar cousin, that is cathode cousin, like silicon, which has not happened yet. The other and obvious thing to do is to use a pinch of silicon. Don't use too much, so that you still have comparable capacities, but better than graphite. So you sort of meet midway, and you can still make a better battery.
Thank you.
Okay, maybe one last quick question. Please.
Students.
Yeah, Professor always encourage the student to ask questions.
Any questions from the students? Okay.
All right. So if there is no further question, let's thank Professor again.
Thank you. Thank you.
And then we're going to give a token of the appreciation to the professor. So, Professor Anurag, would you be the honor to, please? Okay, Professor. you very much. Sorry that I'm too excited to be here, so don't know what to say. Let's move on to the next speaker, which is Professor Ajay Kumar Mishra. He's going to give a talk on the nano-engineer material for environmental sustainability. Professor Kumar Mishra is a working professor in the Department of Chemistry, University of the Western Cape, Cape Town, South Africa. He is a B-rated researcher recognized by the National Research Foundation, South Africa. Professor Mishra has published over 400 publications and received more than 10,000 citations. So he's a renowned scientist and very famous. So please, if everyone ready, give a warm welcome to the professor.
Good morning. Thank you for the nice introduction, and the organizing committee has done an excellent job, and especially Professor Anurag, he knows how things can be done and how to bring the good people like we are listening from yesterday, right? So I think you guys watch movies as well. You got the energy. How's the Joes? Right. Okay, so if Joes is fine, you got the energy. Let me try to take through from the energy to environment, right? So we are going to go one by one. I am going to make sure like everybody today is going to take home something from this talk, right? You are going to promise me that you are going to implement something which is going to help to the environment, right? So let me try to see from where I am coming. I don't know anybody in the audience visited to South Africa except me, right? Nobody, right? So that is why I put this slide. You can see many times people doesn't know because of the cricket. Actually there is a country called South Africa, but I have witnessed so many questions like, oh, South Africa, that what is the country name? Because they feel like it's southern part of Africa, right? So this is the most southern part of Africa. I will just take you through so that at least if nobody has visited, you can plan, and then I will move to my lecture side. So the country right here at the bottom, you can see there, and population is closely around 62 million. So you can't compare from India, right? We have mixed races. It's around 80% black population. We have around 7.9, closely 8% white population, and closely 8% we have the Asian population. That brings Indian, Chinese, from Thailand. You can get your local food right there, actually, and you are not going to miss that Century 21, that kind of auditorium what you have in Bangkok, right? So, and if you are looking for samosa, obviously you can get with the name samosa achar right at the south. So you can really enjoy that kind of things. And we have like Indians, before the Gandhis, like around 1860, they have been transported that side because of the sugar cane. So sugar cane is the very tedious job to grow, and Indians are masters with that, and that is why they have been brought there by the British people. Obviously, it's not like ruled by the British people, it was ruled by the Dutch people. Obviously, there is some history as well. Let me not go through there. Right. And I am currently based in Cape Town, which is just, you can see in the tip, I don't know whether you can see. It's right at the bottom, and it's a beautiful city. You can try to see there. In terms of my university, this is the way it looked like. So I just thought if you let me just try to give you a little bit overview there. That's the campus, and this is the building, the chemical science building where we are based. Obviously, like you can see the daily student life. And this is the business I want actually, like at least you can feel more because you got the energy from Professor Rao, right? So now this energy you can try to bring it actually like to see the environment is very good. So this is my approach towards your side, like look how beautiful the environment is looking, and what is your approach is going to make sure like it is going to be good, right? So this is the view of Cape Town, especially within the city. You can see it's very small cities, not a lot of people are there, but it's very well organized. You can see it is nicely done. And if you follow some typical comedy show by Trevor Noah, I don't know whether you know, he's the Hollywood star, I suppose. Those who's working in US, you already know that. And he's basically South African. And one question came for the Tesla car. You know the owner. Obviously, he is also having the background from South Africa, right? In science and technology, I'm not going more details, but we got few Nobel Prize, especially first human heart transplant. It also happened in South Africa, especially in Cape Town University. So there is a point in literature they have around a lot of Nobel Prize they have win there. So what you can see actually, like if you want to look the good penguins that side, especially if you come to Cape Town, we have a town called Simon's Town, and you can easily see actually like I had the video, but just for the sake of time, I just thought actually like let me just give you the picture. You can really play with them and you can enjoy. So this is called African penguin, not looking like you are going to ask like okay, penguins are not visible, it can't be found, but it was also discovered in 1989 where only two penguins was brought. Obviously, it was brought from Antarctica, right? And then from there, now we have a lot. And then you can easily see from there. That is the very famous island. I don't know whether you follow some South African history called Robben Island, where Mr. Mandela was kept. Obviously, he was jailed in 27 years, but obviously, he has spent actually quite a lot of time there. So still that is like a tourist attraction. People go and try to see there. And this is the most southern western point of Africa, Cape of Good Hope, where you see the Indian and Atlantic oceans meets. Not exactly the same point, it is still like around 40 minutes drive. We call it Hermanus is the place where you will be doing. But for the sake of tourists, I think that is the destination has been planned. There is a lighthouse, and if you are trying to look nice coast streets, you have to walk with them, and you have to walk, watch their legs, right? If they hit you, you are done, right? So that is the beauty. I also wanted to show there, so that when you are coming, you can do. But typically, if you talk about Africa, you talk about the safaris, right? So the safaris are very good. You want to walk with the lions, like interaction. I think this is the place you must come, right? So it's one invitation to you to come and see the lions, and especially if you try to see these wineries. So especially the Western Cape is very much famous for the wine production. I have actually a few wines whenever I travel. I try to carry with me. And it's not like I need it, right? So somebody needs it, right? So this is the winery you go, and when we do the conference next time, when I'm invited, we always do our banquet or dinner or anything planned right there. Within, you can just walk through and you can enjoy. You might have watched that movie called Zindagi Na Milegi Dobara, right? So you have seen that scuba diving, skydiving. I think Cape Town is the place where you can try to do there. And this is the, what I try to get it there, because that wine used to be ordered by, I forgot the name, right. Mr. Napoleon, now I got it, okay. So Mr. Napoleon used to buy, and the whole crate used to be coming there. This is the one I try to get the picture. It's quite sweet wine and you can have it, right? But in terms of the food, we have like a typical good culture, like all the mixed European, American, all the culture. So we have it, and there is a lot of names are right there. But what we try to do it like whatever it comes, whether you are having sorrow, you are having some achievements, we always do the braai. In India, this is called barbecue, right? But there we have a simple terminology called braai. So we brought the people, with obviously, all kind of stuff you can do. You can bring it from your home and then you can enjoy right there. This I think whenever you visit to South Africa, you must enjoy that because it has been invented by the Indians. There is one language is called Afrikaans because we have total 11 official languages right there. So in that, one of the languages is called Afrikaans. So in there they says make a plan, means they are going to make a plan for anything. But for Indians it is known like we already have the plan. So you know the history like around before 1976 there was the apartheid region where people used to get the food on their hand. So they used to get the bread. So you can see like how they have discovered. So India they make a hole and then all the curry is going right there. And this is very famous in South Africa called Banija. So if you are coming there, you must enjoy that. Okay. Now, I think that was my take home number one. Okay, from everybody. At least now you are free mind, like at least what you can think about South Africa and why you should visit, right? It's not like you have to go over the work, right? Now I'm going to see you like how you are thinking about the environment, right? Once you are trying to think about the environment, we are looking about the water, right? And why this water is getting so important, right? You see like there is an ocean, everywhere is covered, it's around 97% it is covered, that ocean. But the real availability of the water is close to 1%, correct? So there we have a lot of bigger problems in terms of the accessibility, the purity. And we are in danger zone, including Africa and also the India side. So the idea is like how we can try to find a solution where we can try to clean the environment. The two ways of going, one is your way, who is not working in the area, one, what we are doing as a scientist, right? So I will go two ways, but this is only slide I try to put it for your, take home number two for today, right? So what I'm trying to say, like, try to make certain kind of, pamphlets within your office or home where you can say no to plastic. I have done one BBC interview in 2016 where we are trying to use the plastics for the purification of water. So if you want to follow, the interview was done by Rajan Detta, and it is Plastic Exchange the World. So obviously you can try to see where we try to encourage this kind of, pamphlets where you can do, right? But if you have to see like what pictures I give you, like it's less than 1% of water is available, what we are trying to do with our daily business, right? If you try to go with your number one, number two in the morning, right? Have you thought about like how much water you are spending there? Okay, so if you are doing like the big flush, the typical one used to take around 17 liters of water, but nowadays it's around 7 to 9 liters. That is the way the water is getting consumed, right? The other one is around 2 to 3 liters they are doing. So when you are trying to go with the wise one, because you don't know a fact that I think one of you has raised the question about the zero water in Cape Town, so where we were helpless to use almost like no water. People were allowed only to take bath once in a week, right? Even like if you are going for number two, you are only going to be flushed after 2 times. So there was so huge, restrictions, and when we had that JoJo tank. In India, we have that syntax kind of, tank, but we never had that concept because we never know we are going to have that kind of problem, right? In terms of like now we are in winter, if you try to see number two, I don't know whether we have part, but it's fine. So number two, like when you are going to go and try to take bath, don't put your hand right there, put a small bucket, store that water and use it for your flowering and other kind of things, right? Then if you are washing the dishes, if you make it in COVID time, we have done quite a lot, right? So you can try to also minimize that way, like if you are using that way. Then this culture, like the bathtub, is not very common in India, but in South Africa, it's like a little bit fun, so people try to do that. So obviously, if you are using, we encourage like go with the half. Now, among the audience, you can also try to see like how you do your repair kind of thing. Like once in a year, you put in a calendar just to see where there is a leak. If you also see some water is leaking from anywhere, you can just try to report so that it should be taken care. How it will happen? It's your responsibility, right? That is why I say this is takeout number 2, right? And then if you want to have the fun, there is a water park. I have seen actually even this side it is happening. So please do that. Okay. So that is your part who's not working in the environment field, not working with some developing material and going for the water treatment, and that's how actually like my part comes in. Like my means the whole research group. If a lot of students are involved there, they are doing the projects. I'm going to go one by one, and I will ask chairperson when he put his hand like this. I know it's like 10 minutes is remaining, right? So please give me some time. Okay, so that I can make sure like you are well taken care. Obviously, there is other sessions as well, right? So, in the typical way, we need to also understand it like how, when you open the tap, how the water is coming, right? So, you need to see it like these are the processes it is going through. There is a big channels are there, people are using quite a lot of membranes. I don't know whether you heard this terminology. Anybody heard membrane? Are you using somewhere? In every household in India, that is the biggest one. We call it RO, right? When you see the Hema Malini is giving that ad, King RO, you are so happy, but you don't know this is coming from the membrane side, right? It's called reverse osmosis process. So we have developing quite a lot of membranes, the ultrafiltration, the nanofiltration, then we have the reverse osmosis. Obviously, we are doing some desalination project, but today I'm not talking a lot of those things, rather than I'm just trying to see if you like how it happens, and both the municipality, the industry, they are all together. So today's talk, what I am trying to begin now, it is going to be focused on how do you look like for your good clothes, right? So that is we are trying to talk about how you can try to take out your textile, waste removal right there. So this is like a way, basically the wastewater treatment plants are doing, where we have rainwater in South Africa, and Department of Water Sanitation is directly involved in our project. So they try to provide certain kind of this information, especially when you go to industry, they try to flush the water, right? Once they are flushing the water, you are not going to get the real waste. So obviously, like that sample is quite important if you try to follow all the procedures in the wastewater treatment, especially the primary and secondary treatment, right? I think that will be like little bit not coming to your mind when you are going to see this picture, right? So this picture, especially this side, if you try to see, this is coming all the way from the municipality. There is one 82 municipality in Durban, which is there, but this one is directly coming from the textile company right there. Okay, so there are different kind of dyes that they are using. Those who are working with the textile department, obviously you are knowing if you like there is a different kind of dyes you try to make it because you are looking for the good fabric generation, right? And then when we are trying to look, we go for the sampling. This person, if you try to see this guy, he's from the government, so he always try to take it so that the security guard is not going to say that you are not allowed. So we go with there, we have our water kit where we try to see all the physical parameters like the TPS, then we are looking at the pH, then we are looking at the total suspended solids, right? So how it is there, and we try to ensure it like all the parameters we are trying to capture right there. So we used to go with the freezer. With that freezer, we try to keep the samples and we freeze it, and then when we ready, we try to analyze and see if like what kind of solutions we are going to provide. So as I mentioned, if you like today's talk, I'm trying to focus more mainly with the textile. We do with the AC. Oh, those. So the acid mine drainage project we are doing with the heavy metals. with the ESCOM, the power company, we need good water. So obviously, we are looking. So the whole idea, what is lying there, the pH, how we are going to maintain. Because if you try to typically, I don't have anybody visited any textile industry near time. So if you try to see, like they usually use the sulfuric acid solution and they try to manage the pH, right? So they try to manage the pH from neutral pH like around 7 to 8, and that's how they try to discharge. And what our job is it's not like you can only maintain the pH. We need to also look into what are the other contaminants there, like where you are making the BOD, the COD, and then the TDS, So all those parameters when we are looking, especially the after treatment and when we are trying to discharge that one, that is very, very important. Since I have been warned, so I have to go a little bit faster. I should have managed my time. Sorry for that. Right? So here, there is when we are trying to talk about this the treatment, we have like the physico-chemical method, the chemical method, the biological method. We are not going there, especially the biological methods, but we are trying to do with the physical method where we have the adsorption and the reverse osmosis. And then with the chemical method, we have the photocatalysis, that is the most easiest way to do it. And then the ozonation, that is the device we have generated with the help of my Russian counterparts. So it's a simple device which we make it and we try to put it, but it was only working with a certain flow rate and obviously like a certain kind of the volume. So that is there. So the idea is like if you try to talk about the photocatalysis. So here what we are looking to like when the sunlight is falling on the surface, you see there is a holes and the electrons is generated. Both are the one who's participating in terms of photolysis of the degradation of the dyes, right? The idea what we are trying to look into like whether it is going to be highly efficient and whether we are going to use the direct sunlight, right? So bigger challenge what we are facing, if you try to see different kind of materials what has been delivered, people are still doing with 400 to 800, that is the visible reason. Our approach is like if you try to bring it to direct sunlight, they are trying to go with the ultraviolet region, which is 200 to 400. And our approach is like we have to go with the visible region, which is 400 to 800, right? The reason is like you can directly get the sunlight, and the sunlight usually has around close to 55% of the visible light, and then you can easily degrade your materials right there. So in terms of like when we are trying to put your material, there is the component what it is coming there in terms of the decolorization and degradation. So those two concepts has to be coming right in good pictures in you if you like how the material is going to be strongly hydrogen bonded or it is weakly. If you try to see from this side, when there is a strong hydrogen bonding, you can see it's around 97% of decolorization, means the color removal is happening. And when we are trying to see from there is a weak kind of hydrogen bonding is happening, you can easily see like there is a around 33% color removal, right? So the idea is like what we can try to design. So what we have done is like we have made one material. We are working with the Honda group with this project as well. So where we are trying to make some doping of the rare earth metals, right? And we have the multi-wall carbon nanotubes. So and the base material is the titanium. Obviously, anybody who's working with the photocatalysis, you know actually the titanium has the most abundant material for the photocatalytic degradation, right? So we try to embed with the multi-wall carbon nanotube. We did with the single wall as well. Obviously, with the whole process, we have also generated a CVD mechanism within our lab. So where we are trying to make the carbon nanotube during that process. And then obviously we have embedded the erbium, that is one of the rare earth elements is there. And you can see it's around 99% of degradation we have achieved. But this is only for a specific dye, we call it reactive red 120. It's called RR120. So that is the dye we have tried to remove there. The three-way of the mechanism, when it is coming right there, you can see like itself with the titanium, how we are trying to see, as I say, like when you degrade it dies is basically the organic compound, right? It's a basic way to understand. And when you are trying to, again, if there is a some minerals like some nitrogen and sulfur groups, we have to also see like how we can demineralize, right? So with the titanium, we can also try to see like it is degrading and converting to the water. And the CO2, obviously we have also the solution to what we do with the CO2 and water as well. Then we made with the second step with the carbon nanotube. And this one is going like we bought directly from the sigma average. Also with the CBD method, we try to see like how the competitive it is happening, right? And the third one is when at the top you can see like this is the reactive, iridium. When we try to put there, obviously we achieved a lot. So in terms of like certain the parameters when we are looking the XRD, we try to look like what are the fields, whether it is a amorphous or crystalline. Obviously, we are not expecting any lot miracle to be very crystalline material. Obviously, these are quite amorphous nature, and we do all the morphological studies with the SEM, the TEM, to see if you like how the material is going to behave, because that will be directly proportional to see if you like how the degradation we are going to achieve. So important thing is like I'm not displaying a lot because I wanted to cover so many things, but the idea is like what we are trying to do with this is like how we can do the 100% degradation, and also how we can maintain the time in terms of 100% degradation we can do it. So you can see with this material, it is like 180 minutes, which is not very much feasible. And we have published this one in JPC, actually a good citation is happening, but the bigger challenge actually what we could have achieved if like this one within 10 minutes time, right? But this one is taking 180 minutes, that is 3 hours. So obviously like for the publication it is good, but for the sake of like we are trying to look for the prototype, we need to do. So for that one, what we have tried to do is like we try to play around with the phase change in the titania itself. So those who are working with the titania, it is 5 phases they are doing. Basically, the rutile and anatase is like most common one. But what we have done actually in this one, we try to see like how much band gap we can change of titania, right? You might be knowing like it's around 3.2, 1 somewhere the band gap of titania, and we wanted to reduce this as much we can try to do. So in this one, there was one master student who came and he says, why not we are using some halogens? So I said, okay, that is a good idea, let us try to do. So we first time we introduced the sodium chloride right there, and in this combination what we try to do is like when we are doping with iron, titanium, and obviously the sodium chloride. So if it is going like around different kind of percentages, like you can see in this one, this is the absence, the first one. The second one is like when you have the 10% of sodium chloride doping, and then we have the 25%, right? So this kind of stoichiometry, when you are trying to change it, obviously you can see it like how the phase is happening, the changing from rutile to anatase, rutile to anatase, are again the last one is like again rutile to anatase. But the bigger dramatic picture of what is coming right there, you can see from this slide as well, like the diffraction patterns. You can see like the nature, the phase. You can also see like the small differences coming right there. It's not like big dramatic changes happening. The TEM obviously like you are also not expecting a lot, but the bigger change what you are looking right here is the band gap. So as I mentioned, like the titania itself had 3.21, but when we try to play around, like the kids we play with the dough, play dough, they do, right? So when we play around, you can see the band gap is almost half. It's like 1.67, and we need to reduce the band gap quite lower side so that we can maintain the synergistic effect, and obviously that will be helping in terms of degradation of compound. Chair will take another 5 minutes if you don't mind. Yeah, thank you. Then we have certain kind of other projects what we are doing with the approach is like in this kind of project, like if we try to make like the material magnetic, so that will be quite easy to separate, right? And then we can do a number of cycles, and number of cycles is quite very important, and also we can maintain the strength of the material, because if the strength is still not maintained, then obviously you can go number of cycles right there. So we have some cobalt ferrite based titanium we developed. Then we are also developing some mesosferous material where we have some zeolite, silica, and titanium. We are trying to play a role. And then obviously, like today, what I have not covered about the membranes, we are using a lot like reduced graphite, the carbon nitride, the graphenes one. Obviously, like we are trying to make the reverse osmosis method actually just to make different membranes. So I think recently one or two PhD have just completed the project with the membrane project, and then there is a lot others actually who's working with the composite project, the nano composite project, and then obviously like the material development. So the bigger approach is like is coming from our side actually like we can develop the material which can be sustainable. And that again goes with the United Nations goal. We have the Sustainable Development Program. I think Professor Abuza was trying to say in the beginning. And then we are looking in that way so that we can see if our environment is quite clean. So the approach is very simple. If we are trying to take ourselves very handsome or beautiful, right? We are looking for good clothing that come from the textile industry right there. So what we can do, the approach is like we can do the degradation, right? Once we are doing the degradation, then typically we can get the CO2 and water. The CO2 we can typically put, I think Professor Rao was trying to give very good idea actually like how we can go. Typically like you can go the reduction mechanism to make some alcohol out of it, right? Or you can, so that is the way we can try to see the CO2 utilization after the degradation. And the water, obviously, we are looking for the future Tesla cars, right? So water we can further split, but again, the time, the temperature you need quite high. The storage is like a huge kind of solution is there. So what we are going to look there. So end of the day, when we are looking actually, we used to have one of the project like where we are trying to collect some waste material called parthenium or hyacinth. So we try to collect it, we try to see it in different way, and obviously we have the carbon, and we go with the same electrochemical method actually, and we try to make a beer. So every Friday it was like a beer tasting. So people were invited and quite enjoyed. So the approach is very simple, like how we can do this material like more usable, and then how we can go with the lab scale to pilot scale. Just for your information, we own a community. It's like basically this is community-driven project where we have put 500 liters of the waste directly comes there, and we put our membranes, and then we filter it, we maintain the water quality, and then we try to have the certification, and that's how we distribute. So this is the way we are trying to go there. But obviously there is certain industries quite interested to make it at a bigger scale. But obviously like that is ongoing process we can do. 2 more minutes here. I read the IEEE now actually in the nanotech technology side. So there is funding available like around $1,000 if you are trying to organize a workshop or something. It is going to be multinational. So anyway, from India as well, like if you're trying to do. So since I'm heading, I have that one, so I can do. So if you are a member, you can apply, and that's how you can do. The details you can try to get it right here, directly with the website. We have also a consultancy company we registered. It's called Academy of Nanotechnology and Wastewater Innovation, where we try to go more on the summer school, the teachings, conferences, the nanotechnology programs we try to do. The idea is like we are trying to develop a different kind of material. You can see there, with the jobs on nanomaterial development, the photocatalysis, the hydrogen generation. So that is the company is doing. Expertise we have actually like as I was trying to mention during our breakfast time of how that we are developing the silicon carbide based on the pulp and paper effluents. So that is the picture coming from right there. This picture we also get it the patent is already in process. And then this one is also very interesting, like we are doing by our company, like you drink the beer or the wine, right? And the glass is quite like colored. So we try to extract the dyes out of it, and the same thing the glass we try to combine carbon source from any waste, and then we make silicon carbide out of it. So that is a different multi-project we are trying to do there. And then obviously with the project development, outsourcing, so this is the way we try to do it. Certain references like what I have been introduced, which is there, you can just try to follow with this. And then I have to thank you many people and then some of them I not updated, I have to apologize for that. And then that's how I want to stop and welcome any kind of queries.
Thank you, Professor. I think we still have time for a quick one or two questions. So, please. Okay, please.
Thank you, sir, for such a nice, wonderful lecture. And most of things were now polluted too much. So whatever materials which you are talking, carbon nanotube or TiO2, these materials are very costly. If you are going to, so far research point of view, these materials are very good. Because if I am going to purchase, let us say, 1 gram or 2 gram carbon nanotube simply from company. So my question is that as expertise in this field, do you think there are some alternative materials which are going to play a vital role in this clarification or maybe cleaning process and other things?
I think it's a very nice question, and I think I encountered this question several times, especially because I graduated from the university. So I know, and then I often goes there and people ask this question. So if you are looking the sustainable solution, the cost effective, obviously you are not looking this bigger solution. But if you try to look the way the RO system is working, obviously you are looking into a certain ways there. But your question is coming from the Yamuna side, which is the bulk kind of problems we are looking there. So obviously, we need a good engineer just to see how they can segregate the solid waste, because it's not like one kind of component is there, right? Only dyes are there and heavy metals are there, right? There are so many components are there. So I think if you recall, we used to encourage our students to go see municipality how they are segregation mechanism where they try to segregate the solid waste. Then when it goes to different component, they try to channelize. I think in Bangalore they have this kind of mechanism, like with the house waste they have like a different component, like 1, 2, 3, 4, like you can battery you can put it here, the paper you can put it here. So they have, but other side I have not seen that mechanism. So if that segregation is there, then obviously we have to go for the dilution mechanism. Once that dilution is there, and obviously we can apply that material. So solution is there, and obviously the cost, obviously we are not going to put a lot of, because the project what I say, we are using like 2%, 1%, so it's not a lot of materials we are trying to use it. And if you are looking for good solution, obviously we have to invest. That's how we are going to find that.
Okay, thank you.
Thank you.
One quick question.
The students, they are so quiet. Professor Rao was also not happy, and I don't want to go together with him. I just want to say, at least you say, what is my name? Just ask, right? So ask any questions, right? Yeah, please, go ahead.
Sir, in your thank you, sir, for the nice talk. So in your publication, you have shown that it took 3 hours to photograph. You how much time it will take and to complete treat the wastewater.
Right, I think your question goes even more basic to see that I didn't disclose it, like what was my synthetic water solutions, right? With the textile dye, when we try to collect it, what was the real waste concentration we had it. So we are looking around 100 ppm or 200 ppm concentration right there. So if once you are going for the real waste, we are trying to look into like what are the concentration is there. That's what I was when I was responding you know, to you, and I was trying to say like it has to segregate it and then it has to go to dilution mechanism. Only then we can see into like what solution based on our materials we have developed. We are not champion, we are in science, right? So we are trying to put solution obviously with the publication or the many other ways, but when you go to the industry, and that is the big challenge is there, like the academia and the industry, right? So when you are going there, you can see like there are so many challenges they have it. So obviously, when you are looking from the synthetic to the real waste and real waste to the pilot scale, there's a huge, gap is there. And obviously, like we are working on there, but many times people are not interested. So especially otherwise, if we give the real data, obviously the company will be shutting down. Same thing is here. If you try to go take a taxi via the Yamuna side, you say you can how the discharge is happening. Even the Ganga River side as well. I also try to see. We have a project with Professor Pandey in Allahabad University, and we took our few PhD students and we went to the Sangam side. So they were saying like we are in the tour. I said no, we are not in tour. Let's take the boat and let's try to move around and see how things are there. And then when they see like we are putting thousands of flowers, garlands in the rivers, and then they say like when I was trying to make it, I could have spent more on the research than that one, but because that important role you have to play, like how you discipline yourself. If you try to minimize the waste, that's how our solution is going to come. But if you don't minimize, obviously, it's like the system is not that favorable. Right?
Okay, I think it's about time. So thank you, Professor, for realizing us to love our water more. Thank you, Professor. And as a token of appreciation, I would like to give him the token of appreciation.
Thank you so much.
So it's a break time. So let me conclude the session. Thank you, speaker. Thank you for listening today as well. Thank you very much. And go to the break. Thank you.
So let's thank the chairs here as well. So thanks to the speakers and also the same place, convention center, and we'll continue the discussion during the hall, other technical session, hall 1 and hall 2. Thank you so much. And we also have a group photograph there itself at the convention center.